Yes. Hi, hello. I'm the founder of this brand. Nice to meet you.
Nice to meet you, Camilla.
Okay, so it's a really important day for us today. So here are kind of the product we're producing, and we would like to know how could we minimize the number of workers we use to produce these kind of products.
Okay, explain a little bit about the company. How many workers do you have, and which type of workers?
Oh yes, sure, let me check how many workers. So we have exactly about 115 workers, and you have to know that we have some skilled and semi-skilled workers. Yeah, do you need anything else?
No, it's okay.
Thank you so much.
So to solve the problem of the company, I've created this equation. It's the labor equation. So I have L, X, Y. We have X, the skilled workers, and Y, the semi-skilled. So she wants to minimize the two types of workers. So I did this equation is we need to find a point to minimize the labor cost. So the points are, we need to derive the first so as we can see, this is equal to 0, this is equal to 0. So now we have a system of equation, and we need to find when this one is equal to this one. So we have 3x minus 2 minus 2y equal to 0, and 3y minus 4 minus 2x equal to 0. So now we can see that we have this one that is equal to this one, but this is negative, so we can add these two equations. And we can find that that x is equal to 6 and y is equal to 8. So these are the 2 points.
Which means that to produce a product, X will be equal to 6 hours for the skilled workers and 8 hours for the semi-skilled.
Exactly.
Did I understood well?
Okay. So to know if those 2 points are the minimum or the maximum, we should use the second order condition using the John matrix method. The John matrix method is A, B, B, C. So to find this number, we know that A is greater than 0, so we know that is or a local maximum or a local minimum, and then we have AC minus B is equal to AC, so we have 6 minus 4 is equal to 2. Yes, to 2. So we have A greater than 0 and AC minus B cube is I have also AC minus B square is greater than 0. So when A is greater than 0 and also AC minus B square is equal to is greater than 0, we know that is a minimum.
Okay, perfect.
Thank you very much for this opportunity to work with you.
So first of all, we have to begin with learning what is f of c, so first order condition. So first order condition is when, for example, you have a function f and you want to find the function in respect to x, so this, and then in respect to y. Then when you found the numbers of each of them, you will have to make a system with f of x up and f of y down. And with this system, we're going to find the stationary points x and y. To continue, we're going to do the second order condition. So with this second order condition, once we found the points x and y, we are going to understand if they are maximums or minimums. So to be able to do so, we have to do the John's matrix. So it's A, B, and B, C here. To be able to find the values of this matrix, we have to find A, which is f of x in respect to x and y. Then we have to find B, so it is f of xy of x and y. And finally, we have to find C, which is f of yy x of y. So to be able to know if there are maximums or minimums, we're going to use 4 formulas.
So the first one is if a is smaller than 0 and ac minus b squared is greater than 0, then x and y are maximums. The second one is if a is greater than 0 and ac minus b squared is greater than 0, then x and y are minimums. The third one is if ac minus b squared is smaller than 0, then x and y are saddle points. And finally, the last one is if ac minus b squared is equal to 0, then x and y can be either maximums, minimums, or saddle points. This means that x and y are inconclusive.
We are now going to see another example that we could be useful in the everyday life. For example, in the weather forecast conditions. So it's how variable optimization can be used in order to calculate the highest and the lowest temperature of a flat region such as this one. So we have 3 entries. We have the shape of the regions, we have the boundary, and we have the temperature function, which is here. In order to reach our goal, we want first to find the local maximum and minimum point in order to reach and to find the critical points. So once we've derivated the partial derivative, we find those x's and y, which are the 2 critical points we're looking for, and at those 2 critical points, we implement them into the temperature function, which gives us the temperature at those points. While using the boundary equation, we're gonna solve with the result of 2 endpoints, which are those 2 ones. Then we'll implement them into the temperature function, which is leading to 2 results, 5/3 and 1/3. Now we have to find any extreme value located in the interior of the upper semicircle. Then the temperature function will be used again, but the y will be replaced by its value found up here. So basically we find this equation. And we will need the partial derivative of the new temperature function to find the extreme values. And so with the boundary function, we're going to substitute the x value we just found to find the extreme. So once we substitute this number, we find a new value for the y, which will help us when included into the temperature function once again, to find the temperature in the 4 candidates to find the highest and the lowest temperature. So when we resolve this equation, we find another 1 candidate. So in the end, we're left with 4 candidates. So the first one we found, which is -1/9. The second one, which is 5/3. And the third one, 1/3. And then with the last one, 55/18. And so in other words, the hottest is definitely this one. So this will be the hottest temperature, and the lowest is definitely -1/9. So now we have our 2 temperatures, the hottest and the lowest.